Good morning, everyone. Today, we're going to be extending the idea of volume into what we call washer method. So a lot of what we did with this method is going to apply here still. We just have to do a little bit extra with our formula to adapt to a slightly different object in terms of its volume. So, okay, you guys have the notes in front of you. Let's review this method first. So this method, we always start off with some shaded region. So two days ago, we did the y equals square root of x. So, and rotating it about the x-axis, you guys can indicate that with our shaded region there. And we're always, in this case, this problem is rotating around the x-axis. And as it rotates, we can imagine that this shaded region is going to end up being below the axis as well. It's going to kind of, in a circular fashion, kind of form an object. And that object, we can think of it as the sum of circular disks, right? And that's why we're able, that's why we understand where that formula is coming from. Formula is coming from the fact that we are involving the radius or the area of a circle, and we're just accumulating these circular disks from one end to the other, and they all have different shapes depending on how the graph is rising and falling. Okay. But one noticeable thing is that we only needed one radius because there was no gap. There's no hole to subtract out. This object is going to be solid. There's not going to be any give. There's not going to be any indentation or any hole or any, right? So there's nothing that we need to, yeah, it's just going to be a solid cylindrical disc from one end to the other. Okay. So today we're going to see problems where they're more going to be hollowed out, right? And because of the fact that they're hollowed out, our volume formula needs to be adjusted. We have to basically subtract out that missing portion that before was not an issue. So let's look at this figure here. We're going to look at it in more detail, but right now I just want to talk about it from a big picture perspective. Look at how the shape is. This is kind of like a leaf-shaped shaded region that is kind of pointing up at a 45-degree angle, but we're still going to rotate this around the x-axis. But see if you can imagine what this is going to end up looking like. As we rotate this in a circular form around this dotted line, you can kind of see and visualize that it's not the same as before. I know we're not looking at the same graph as before, but there's a distinct difference, right? That difference is the fact that we're going to have this hole, this gap. And so rather than thinking of this as adding infinite numbers of circular disks, the better representation is thinking of this as adding infinite numbers of circular rings, right? There's still that circle portion evident because of the rotation, but we have to adapt for all these missing gaps that we didn't see before. So that's why we call it the washer method. Washer method is another way of saying rings. So circular rings. So and you can kind of see it in this illustration here. And then you can see how the bowl-shaped object, if you were to slice this into many different parts, you're going to see that as you open them up, they're all going to take on the shape of rings, right? Maybe rings with different inner radius versus outer radius, but they're all some variation of rings. Okay. So to give a kind of a two-dimensional representation of this, and also to help us see where this formula is going to come from, let's think about what goes into finding the area of a ring. What information would we need if we want to find the area of this shaded region ring.
Circumference?
Not circumference.
No. The area of the larger circle and the area of the smaller circle?
Yep, and subtract it, right? That's basically it, right? We find we need the area of the large circle, and to find our large circle, we need the radius, and to find the area of the small circle, we also need the radius. I'm going to call it little r. So the area of that circular ring is exactly that. It's area of the large circle minus the area of the small circle, and then the resulting area is the ring that you see in front of you. Okay. And that is basically what we're going to be doing with to get to this washer method formula. We're taking this two-dimensional calculation and we're going to extend it to the third dimension, adding a dx and then doing an integral in front of it. Typically, we factor the pi out since that's a common term, and then we put r squared minus r squared. So that leads to our formula that we're going to see here that I have notated here. Pi integral from x1 to x2. And we'll represent big R as a function. So we say big R of x quantity squared minus little r of x quantity squared dx. So if you look at washer method versus this method, it's virtually identical. I just need that minus r, little r squared. But if you cover up that little r squared, you basically have this method. Right? So we're just doing a little bit extra, which means we got to keep track of a second radius that we're going to practice today. Now this formula is built for top minus bottom. Okay. So first page, we're just going to look at it from a top minus bottom perspective, and then once we get comfortable with this, we'll go to the second page and we'll practice one where we got to make some adjustment, a right minus left. But a right minus left is going to be very similar to how we approach right minus left for this method. We just have to do a little bit extra with the formula. Okay. I have some definitions here for big radius and little radius, or how we're going to create these radius. Big radius is the distance from the axis of revolution to the further curve. That's going to be that further distance. That's going to be the, kind of representing the radius of this large circle. Okay. So axis of revolution, we always have to include the axis because the axis is the center of our object. So center. Little radius is the distance from the axis of revolution. Again, we need to involve the center when we draw the radius to the closer curve, to the closer of the boundaries. Okay. Now let's look at example 1 and see if we can follow the formula and build everything that we need to find. Find the volume of the solid created the enclosed region y equals x squared and y equals square root of x revolving about the y-axis. Sorry, x-axis. So the x-axis has the equation of y equals 0, and that's my axis of revolution because I see the word revolving. I know that if I see the word revolving, it's about to tell me where the axis of revolution is. Okay, axis of revolution is at y equals 0. That's where the dotted line goes. And if it helps, if you want to put the fact that there is going to be a bowl-shaped object, and this is that dashed line is the center of your object, and we know that we have to involve the center if we ever want to draw the radius. So if you want to just have a visual reminder that the dotted line is not at the edge of your diagram, it's the center of your diagram. Okay, and that may be a visual reminder that the way you're going to draw the radius has to include that center. Okay. Now, another thing I want to point out is look at how the dotted line is in relation to the shaded region. Do you see how the dotted line for this method is up against a flat surface? You don't see an inch of gap between the dotted line and the shaded region because it's up against a flat surface. But here, even though it's touching, there's a significant gap, right? So basically, if it's dealing with a curved region, no matter how close it gets, even if it's touching, it's still going to be in washer method territory, right? So washer method, actually for this method, the restriction is going to be higher, right? It needs to be up against a flat surface. Anything else is basically washer method, because if there's a gap, even if it's only a gap for part of the portion of the problem, that's enough for us to have to involve rings, involve washers. Okay, so we can tell that even though it's touching, we can see the gap, and that gap is going to require us to need to subtract out that inner ring or that inner radius. So we're going to have to draw a radius now. Our radius is always going to be perpendicular to our axis of revolution. Let me name this AOR, y equals 0. So we're going to draw our we'll draw the big radius first. So let's follow the direction here. Start on the axis of revolution, and we're going to extend our radius to the further curve. So it doesn't matter where you start, just put your pen or pencil on the axis to begin with, and we're going to extend to the furthest boundary of our shaded region. And we're going to name that big R of x. Now here's my suggestion. When you draw your big R and little r, it doesn't matter where you start, or you can put it, inside, you can put it outside. Doesn't matter which one you put to the left or to the right, but just try to put them next to each other. Okay, if you can put your big R and little r next to each other visually, that's going to be very helpful, because they can guarantee you that your big R is always going to be longer than your little r. If you put them on opposite ends of the graph, then the graph may suddenly change to the point where your little r looks to be like a big R, because all of a sudden it looks like it's a longer length, and that's kind of confusing visually. So if you just put them next to each other, doesn't matter where you put it, just next to each other, you're always going to be able to ensure that visually big R is going to make sense. It's going to be the larger of the two. All right, so little r, I'm going to just pick a point relatively close to my axis, to my big radius, and now I'm going to extend from my axis of revolution to the closer boundary. I'm going to name that little lowercase r of x. Okay, questions so far? Okay, we're staring at a vertical radius. If we stare at a vertical radius, we know that we can use top minus bottom. Top minus bottom is the one that we feel more comfortable with, because everything is familiar. The equations are already perfectly set up for it. They're all y equals. Their function form, it's just more recognizable, right? Because we see it all the time. So no adjustments necessary. We can jump directly into creating and naming our r of x and little r of x. Okay, so we're going to create our big radius expression. We know it's going to be top minus bottom, so let's look at big radius and look at what the top of big radius is touching. Which graph is the top of big radius touching? It's concave down, right? So it's the root x. Yeah, root x. I know it kind of looks like, because the fact that they flip-flop and we're showing the other side here, but the concave down is the root x. Okay, so I'm going to point to it and label it. Okay, so that's going to come first, root x. Top minus bottom. What's the bottom of big radius touching?
The axis of rotation.
Which is y equals 0. Okay. Now, I like to do this here. Always put a parentheses with your bottom function, and then later, if you decide that the parentheses is not going to play a role, you can drop it. But if you always put a parentheses there, it'll be a good reminder. If there's any distribution necessary, it'll be a good reminder to do that. Okay. I know it doesn't seem like a big deal now, but it's going to be really helpful for more complicated expressions. Okay, let's move on to little radius. Also top minus bottom, right? What's the top of little radius touching?
X squared.
Y equals x squared. Okay, so I'll point to that. X squared minus parentheses. Bottom of the little radius, also on the axis, so also 0. Okay. We see the zeros play no role, so we can clean up. We can avoid having to keep a bunch of parentheses in our calculator keystrokes here. So just root x and just x squared. All right, good so far. Now look at the equation that we used. They're all perfectly matched for a top minus bottom, right? Because every equation that we're using is in function form. Y equals root x, y equals x squared, y equals 0, right? We know that these are perfectly set up for our top minus bottom. Okay. We also need to find the what? The bounds. But the nice thing is the bounds are kind of given to us, right? It's kind of shown to us in our graph, or yeah, in the graph here. So V equals, we'll jump directly into our formula. We're stacking circular rings from this end all the way to the other end. So what's the furthest left that we see? 0. So pi integral 0, that's my x1. And my x2 is 1. Okay, I know we see duplicates here, but we're really looking at the x value, right? We're paying attention to the x value here. Okay. Okay, so now we're just following the formula here. Big radius quantity squared. So we're going to put a bracket or parentheses around root x, and we're going to square each radius separately. That's important. Square each radius separately. Don't try to take a shortcut and subtract first and square once. That's different. Okay, minus little radius squared, bracket x squared, squared dx. I'm just following the formula here. We're not going to, there's no need to be creative with our formula. We'll just do whatever it says and just plug in. Okay, any questions here? All right, this is probably easy enough to do by hand, but we're just going to practice entering to our calculator. So if you're using 36 Pro, then just enter it into the same line like you see in front of you. But if you're using an 84 or 83 or 84, I suggest that we enter big R and little r into Y1. Okay, if you decide that you would just enter everything all into the same line, that's fine, but I feel like you can really save a lot of time, a lot of keystrokes if you just do it this way. So, okay, if you're not convinced, just do it once with me, and then you can decide that you don't want to do it later. All right, so we're going to have big R hold, Y1 hold big R. So we're not going to square it, just hold it, just have root x be Y1. Okay. X squared is going to be little radius, so I'm always going to assign Y2 to be my small radius, so x squared. Okay. Next up, I'm going to go back to my home screen. And what I'm going to do is I'm just going to create a template. And once I create that template, I can just always reuse it, and it will just save me a lot of time, especially if I have multiple problems involving washer method. So math 9, I'm going to go from 0 to 1. I'm going to call my Y1, I call my big radius first. So vars, y vars, function, Y1. No need for parentheses, I'm just going to put squared. Okay, that represents my big R squared. Minus vars, y vars, function. Now I have Y2 representing my little radius. I'm going to square that, and then dx. 0.3, that's an exact value, that's fine. Or you can convert it to a fractional value. Math 1. Both will be fine because they're both exactly the same value. One is not the approximation of the other. All right. Anybody have any trouble with this or with the with 36 Pro? Now, the nice thing about putting it in this form for the graphing calculator is, let's say the next problem is also washer method. All I need to do is to go to my Y1 and Y2, change big R, change little r. I can go back. I'll just scroll to my templates, hit enter. My big R and little r is already set up. The only thing I need to change is the bounds, right? So we can save a lot of time if we just do it this way. But the 36 Pro, you're going to have to just keep track of your parentheses. There's no easy way to call different functions, but I think the 84 you can really save some time, so I encourage you guys to do it this way. All right, any questions with example 1? I just created this last period, but I want to point out some common mistakes that students make with washer method. And I'll go ahead and put this into a document, and I'll put it. I'll type it up and I'll put it under today's link. But I just want to show you what those common things are. This is how we draw big radius and little radius. But what do you think a lot of students? What I see, what mistakes students make when they draw radius? What do you think is a natural tendency for?
They still go like from top to bottom.
Yeah, they want to connect these two, right? And that's understandable because that's how we did area, that's how we did this method. But for washer method, we can't do this anymore. Okay, and why is that?
Because you're rotating.
Okay, and this doesn't represent the true radius, right? Because we're not dealing with the center. This is basically saying, okay, that's like saying connecting those two distances and calling out the radius, right? But I think if we can visualize ourselves creating a bottom portion, then we can kind of visualize ourselves that truly we're looking at the center, and that's why we're extending that radius. Okay, so that's one issue that I see a lot of students make. Always include your axis of revolution when drawing the radius for washer method, right? Don't ever connect the two curves. That's never going to be your radius, okay? The second common mistake that students make is trying to do a shortcut with the formula, but we have to square your radius separately. We can't just subtract big R from little r and just square it once. It looks like the same thing, but these are significantly different from each other. So follow the formula and square your radius separately from each other. Okay, another common mistake that I see students make. Third one is your axis of revolution has no role in finding your balance of integration. Sometimes students see the axis of revolution is so far apart, and they have to, they imagine the graph to be so large, or the shape to be so large that they feel like that has some role to play in finding the bounds. But the bounds is only restricted to your shaded region. You're going to find bounds the same way that you did area, that you did this method, that you did washer method. It's just the shaded region. You can just ignore the rest of everything else when you're finding bounds. Okay, so don't look at the axis when you're finding bounds, just your shaded region. And the last one is, just because your axis of revolution is touching the shaded region does not make it a disk method. All right, sometimes I see students, they say, well, it's touching, so that means there's no gap, so that must be this method. But only if that shaded region is a flat surface up against your axis of revolution. Okay, that's the only time that we can guarantee this method. That's the only time we can guarantee there's no gap. Okay, so make sure. So a lot of problems, a lot harder to create a disk method situation than it is washer method, because this method, we got to have that flat surface, and that axis got to be right on that flat surface. Okay, all right, let's go to example 2. Find the volume of the solid created by revolving the function y equals x squared, bounded by the line y equals 2, revolved about the y-axis. Okay, so again, I see the word revolving. I know that must be the axis of revolution, which is y equals 0. That's the x-axis. Okay, so I'm going to sketch these two graphs. We have y equals x squared plus 1. That's just a parabola that's shifted up 1 unit. Make it pretty spaced out to make it easier for me to see my graph. Y equals x squared plus 1, that's just a parabola that's going to go. And I also have y equals 2, which is going to be a horizontal line. Once you draw that horizontal line, you're going to see that shaded region begin to take shape. That enclosed region that we're after. Okay. Axis of revolution, this is where you're going to create your dotted line. Your dotted line will sit right on the x-axis. Create a rotation notation there, and you know your AOR is y equals 0. Okay. Just by looking at this, we should be able to instantly categorize this method or washer method. Washer method, right? Really, the only time that this shape could ever be this method is where? Where is the only place you can place a dotted line and make this this method?
And like without incorporating the y equals 2.
Yeah, basically the y equals 2. Okay, yeah, the dotted line has to be up against the flat surface, right? This is the only flat surface that we see, so this is the only place that's going to be a this method. Everywhere else, it's going to have to be a washer method. Okay, so okay, just want us to be able to, because tomorrow I'm going to start mixing problems up, and we need to be able to sketch the graph and instantly tell, all right, am I dealing with washer method or am I dealing with this method? Okay. Oh, and what if the dotted line was right at y equals 1?
Then would we also be
Still be washer. Okay, good. Yeah, good. So still washer method because it's not up against a flat surface. Okay, so just because it's touching doesn't make it this method. Okay, so we see a horizontal axis of revolution. We know that our radius is going to be vertical. We know we can rely on the top minus bottom formula. So let's start drawing our radius. Okay, put your pen or pencil directly on the axis because this is the center. Technically, after the rotation, there's going to be a portion that's sitting down here. Right, it's going to be kind of a funny ring-shaped object, but this is the true center of our ring. Okay, true center of our ring after that rotation occurs. Okay, pen and pencil on the dotted line. We're going to extend to the furthest boundary of our shaded region, so it's going to extend all the way up here. Okay, call it big R of x. Okay, now moving on to little r, we're going to pick a point relatively close, but again, we're going to start on the dotted line and extend now to a point that is representative of a closer boundary of our shaded region. Okay, if you put them next to each other, your big R should always be longer in length than little r, and that's a good visual reminder. Okay, we're really depending on the location of the radius because it kind of helps map out exactly what we're going to be needing to represent our expressions. Okay, vertical rectangles, vertical radius, we know that we can do top minus bottom. Okay, so moving on to big R, we're going to find the appropriate expressions for them. All right, let's look at the top of big radius. Big radius is touching which graph? Y equals 2, good. So 2 minus parentheses. What's the bottom of big radius touching?
y equals 0.
0. Okay, so top minus bottom, 2 minus 0. Parentheses there, just as a reminder, if there's anything more complicated that is there to help us out. Little radius. Okay. We pick out, we go to the top of the small radius, and what is that touching?
The x
touching the curve, right? So the curve is y is equal to x squared plus 1. Okay, top minus bottom, x squared plus 1 comes first. Minus parentheses. What's the bottom of the radius touching? Still 0. Okay, still 0. Right, from here, we can clean up our radius so that we don't have to enter in as many parentheses. So big R is just 2, and little r is just x squared plus 1. Yes?
So will we ever be dealing with a diagonal axis?
No, yeah, our axis is always horizontal. Oh, sorry, always either horizontal or vertical, never diagonal, right? All right, so we have our big R, we have little r, but is there anything else we need for our formula?
The bounds.
The bounds, right? And how can we find those bounds? Yeah, set them equal to each other. Sometimes the equation may be too complicated where you have to rely on the graphing calculator to find those intersections, or you rely on numsolve for your 36 Pro. But I think it's easy enough for this problem for us to set them equal and just solve by hand. Okay, so we find the intersection, and this is how we find the bounds. And again, the axis plays not a single role in finding our bounds. Okay, just the shaded region. Okay, so x squared plus 1 is the curve. 2 is the horizontal line. We set them equal to each other. Subtract 1, x squared equals 1. Next step, take the solve for x. Yeah, and what happens when we take the square root? Yeah, and that's perfect, right? Because we're looking for two boundaries, and we have our two values right there. All right, I think we have enough to build our volume formula here. So V equals pi definite integral from -1 to 1. Make sure that you're squaring your radius separate from each other. So big R quantity squared minus little radius quantity squared dx. All right, we'll practice entering this into the calculator. But if you have a 84, I would go to y1 and let y1 hold big R and let y2 hold little r. Okay, go back to your home screen. My template is already here. You can just scroll up to when you last used it, hit enter, and we just have to go back and change our bounds. I want to go from -1 to 1, but everything's already set. Hit enter again. Save a lot of time that way. Try to make it into a fraction. It does, so I prefer the fraction because this is more exact than the decimal. Don't forget pi, and then units cubed. Okay. Any questions with any parts of this problem? Are we okay with top minus bottom, drawing the radius, knowing where they go, why we don't find that distance between the two shaded regions? Okay, let's do one more example. We're going to go to the back, and I'm going to change example 4 so that we can explore a right minus left scenario. Okay, so go to the back page. So we're going to skip example 3. So we can just create a little space above example 3 so I can write the formula for a right minus left. So we're going to change example 4 here. But let me write the formula for this method, washer method. Adapted for a right minus left. Okay, volume, V equals pi definite integral. We have to make some adjustments. Instead of x1 to x2, it's now y1 to y2. So it's going to feel very familiar from what we did yesterday with right minus left for this method. So y1 to y2. Our big radius and little radius are now going to be in terms of y. So we represent that as big R of y quantity squared minus little radius, little r of y, quantity squared dy. So if you're doing right minus left, this is what I need to see on paper. Your expressions are in terms of y, your bounds are in terms of y, and you need that dy there. Okay, but what's going to really help us decide whether we're ready to insert into a radius expression is that it needs the form of x equals. All of our equations have to take on this form of x equals. We need to solve for x for every expression, and that's when we know that we're ready to put in, right? This is going to be the method that that's going to take a little bit longer, right? Because our equations are a lot of times not going to be set up for it, and we have to make some adjustments for it. We can't just insert in as the function form of y equals. They need to take on that look of x equals. Okay, so I'm going to change this problem. Because right now this is not adapted for top minus bottom. So if you guys can just change the axis of revolution, we're going to revolve about the line x equals 1. Sorry, x equals -2. Yeah, it's a little bit off the graph, but we can insert that. So if you guys can change the problem, revolve about x equals -2. That's going to shift everything because our axis is no longer horizontal, right? So if you can extend your x-axis, and I know it's not drawn to scale, we're just going to try to mark off -2 enough to have something there. Okay, so draw a dotted line, write down -2. And I'll say AOR x equals -2. So to visualize this, there's also this kind of leaf shaped on this side as well, right? You can kind of imagine this rotation going on, and there's a kind of like a bowl-shaped ring with a complete hole in between, right? But just enough for you to remind yourself that this is the true center of the figure, right? It looks like it's the outer edges of it, but it's actually the center of your ring. So now we can move on to let's see. Can we tell whether this is this method or washer method? Right, gap, right? There's no flat surface. It's not up against a flat surface. This is the only way we can do this is washer method. Good. So we're going to draw our radius. Start at the center. We know that our radius has to be perpendicular to our axis of revolution. So big radius first. I'm going to extend to the furthest boundary of my shaded region. That's going to be my big R of y. Okay. Let's draw our little radius. Start on the axis, extend to the closer of the two boundaries. Okay, these are visual reminders that we're dealing with the right minus left because that's the orientation of our radius, little r. Okay, before we build our radius expression, are the equations that we're using, are they in the correct form?
No.
They're not, right? We need x equals. I know it's easier to just start using this, but this is not the right form. So let's work on this one at a time here. I'm going to point to this outer one, which is x squared. How can we adapt x squared to get x by itself? Okay, square root. Now, typically, when you do square root, there's plus or minus, but this is only showing the positive roots. So it's only going to be x equals square root of y. The negative square root of y is not showing. It's over here, but this parabola is only showing the positive portion. Okay. Now, let's point to the other one here. The other one is given to us as y equals square root of x. And how can I solve for x here? Not square root, just, yeah, just square, yeah. Got it, yeah, square both sides. Okay, x equals y squared. Now, take a look here. Every equation that we're about to use is perfectly set up now, right? We have x equals root y, that's perfect form. X equals y squared, that's perfect. X equals -2, that's perfect. So now we're ready to move on to build our radius expression, right? We have everything that we need. X equals. Everything on the right is ready for putting into our expression, okay? So r of y, big R of y. Okay, let's point to the right endpoint. What is the right endpoint of big R hitting, touching?
The y equals, or root y.
Root y, okay. So that comes first. Minus parentheses. I think the parentheses is going to be helpful here. Left endpoint. What's the left endpoint of big R touching?
The y squared.
Left endpoint, though. Yeah, it's all the way over at the axis, right? Yeah, -2. Okay. And the parentheses is a reminder that we got to deal with the double negative there, which I'll clean up later. Any questions so far? Right minus left? Okay. Little radius. All right. What's the right endpoint of little radius touching? Y squared. Okay. Minus big parentheses. What's the left endpoint of little radius? -2. Okay. Having those parentheses is helpful because we see, oh, I got to deal with the two negatives here. I'm going to clean that up. So big R, root y plus 2. Little radius, I'll clean this up as well. Y squared plus 2. Okay. Do we need to look for bounds, or are they kind of given to us?
Yeah.
Okay. We can tell by looking at the graph, right? But so we can start building our volume formula here. Pi. Okay. We're stacking circular rings, not from the left to right, but from the bottom to the top. And then our bounds are just restricted to the shaded region. Our axis is really far away, but it has no impact on the bounds. So don't look at the bounds when you're looking at the, don't look at the axis when you're dealing with the bounds, just the shaded region. Okay, what's the lowest y value of our shaded region? Okay, it's duplicate, right? But we're really looking at this y value here, right? 0. Okay, what's the highest y value? 1. We see that there, it's a duplicate, but we're looking at the y value there. Okay, now we just follow the formula, right? Make sure that you square your radius separately and that you're squaring your entire radius and not just a portion of it. So square root of y plus 2 quantity squared minus, make sure that you're putting a minus in between because you're subtracting or subtract out the whole, the gap. Okay. You don't have to show the work, such as use substitution or integral. You can jump directly to the calculator to get to the answer, but I am looking for this step. I am looking for the complete setup. Okay. I need to see y's. I need to see the appropriate notation, separating the squaring the radius separately. Okay, so now we can just move to our calculator. If you're using 36 Pro, you got to enter all this into the same line. But the graphing calculator, I'm just going to update my y1 and y2. My y1 is going to hold my big radius. So you have to adapt. On paper is in y, in terms of y, but in calculator, everything's in terms of x. Okay, so I have root x plus 2 as my big radius and x squared plus 2 as my little radius. I'm going to go back to my home screen. I'm just going to scroll up because I've been using the template for washer method a few times now. And I'm just going to go and update my bounds here. I'm going to go from 0 to 1. But I don't have to play with my expression here. It's already set up for washer method. Okay, see if it'll convert to a fraction. It doesn't, so the best we can do is round to 3 decimal places. Oh, just to kind of remind you, sometimes an answer choice on the multiple choice question may have the pi inserted into the answer. So if that's the case, if it's not showing 1.633 pi, then your answer is going to be 5.131. Because the answer choice already merged the pi, multiplied it into the expression, into the numeric value. So this is more exact than this, but just be aware that if your answer choice doesn't have the pi, it's because it's been multiplied. So just multiply that through and you can find that answer choice. Okay, how do you guys feel about right minus left for washer method? Okay, so I think the good thing here is there's not a lot of variety, is that if you understand the basic structure, you can kind of follow it through every time. And we're just going to practice with that tomorrow. I'm going to try to remind you of some of the pitfalls that students experience, but I'm going to start mixing this method and washer method. And I think by the time we draw the figure, we should be able to instantly tell, okay, am I dealing with washer method or if I'm dealing with this method? And from there, we can decide whether we want to do 1 radius or 2 radius and practice with the formula. Okay, so tomorrow is practice day, but hopefully you feel good about the basics of the setup. All right, thanks everyone. Hope you guys have a great day. See you guys tomorrow.